Hi there guys, well welcome back. We're working towards 4T now, and 4T is all about kinematics. And I guess that you could get away with doing the whole of this by just knowing this little formula here, which I've just stolen from one of the formula boxes. Okay, so if you know that acceleration is the derivative of your velocity, in other words, the rate of change, not dt, sorry, dv dt, so how your velocity is changing over time, you know that the acceleration is that. And here, by the way, we're saying this is a function in terms of t, so we could still say v is in terms of t there as well. I've just left that off because you wouldn't normally put it in a derivative. So if you know that acceleration is the rate of change of your velocity, and if you know that your velocity is the rate of change, not of a, of your displacement, or your distance if you like, how much your distance or your displacement is changing over time, then you've pretty much got the whole of this exercise and this section covered. Okay, kinematics though is basically our way in mathematics of talking about the relationships between displacement, velocity, and acceleration. And when we're talking about displacement, we simply mean up and down a line. So we're saying, well, here's our origin, and we can say, well, one is maybe at 1 meter away from the origin in the positive direction, and -1 is going to be 1 meter away from the origin in the negative direction. So if you like, you can think about this like a train, going up and down the tracks, and how far we're going to be away from the origin or how far backwards. That's our vector movement there. It's got both distance and it's got direction. It's just up and down the track. We're not dealing with things in 2 dimensions. So we're not saying, we're moving around, the place, as a map looking down. We're not moving around in 2 dimensions. We're not moving around in 3 dimensions. We're just moving up and down a line here. Okay, so yeah, I also talked about this in terms of vectors. So in terms of vectors, these are all vector quantities. Okay, so for example, your displacement is a vector quantity because vectors have both magnitude, so distance if you like, and also direction. And for us, the direction is either going to be positive or negative. Okay, so we're either going forwards or we're going backwards. Well, actually, that's what velocity is talking about. And your displacement is saying, where are we on that number line? Are we somewhere at +10 or are we at -5? Our direction means we can be somewhere up and down the number line, essentially. And when it comes to velocity, that's also a vector quantity. But the magnitude of velocity, so we can say the modulus of this will tell us the magnitude of this, and that will give us speed. So speed is different from velocity because speed doesn't have direction. So again, we're talking about velocity being either going forwards or going backwards. So positive going forwards and and negative if we're going backwards. Again, if we were going to do the modulus of S of t, that's going to give us distance. Again, the distance away from the origin, again, if we're sort of -1 there or 1 there. If I said, well, what's the distance away from the origin if we're at this point here? We say, well, we're 1 meter or whatever units we're going to use away from the origin. In terms of displacement, we'd say we're at -1. Now, acceleration is also a vector quantity. But when we say the modulus of this, well, that's still, in everyday speak, we still say that's our acceleration. So you could still say, well, we're accelerating in the car at, I don't know, 20 meters per second. I mean, that would be vast, wouldn't it? I know, maybe 1 meter per second. Maybe we're increasing our speed by 1 meter per second every second. Okay, now we could be going forwards and increasing that speed, or we could be traveling the other way down the motorway and we would still be talking about our acceleration being 1 meter per second, or 1 meter per second squared. So in everyday language, we still use acceleration, be the magnitude of acceleration. But here, when we talk about negative acceleration, that will mean that we are decelerating. But also, if we're traveling backwards and we're decelerating, that will actually mean that we're accelerating backwards. So that's kind of a little bit confusing there, but essentially, A of t is also a vector quantity. Okay, right. So some of you might be aware from physics some formulas which relate A, V, and S together. Some of you may be aware of the SUVAT equations. Now, the SUVAT equations are not the same as what we're talking about here. So SUVAT equations, if you've heard of them, come from this situation. Here we go. Let's just draw it out. Talking about are starting with a velocity of u and ending up with a velocity of v. That's our final velocity. Okay, at the end of this situation, and we end up with a time of t. That's our final time on the axis for time, which we might also call t. But these are kind of simplified formulas which we're using here, so we're not using another letter to stand for t there. T is sort of at the end of this time period. And we've got our acceleration here, which is going to be constant. So over that time period, the acceleration is the difference in the velocities. So the final velocity, take away the original velocity and divide by the time. So say, for example, I don't know, we've got, we finish at 10 meters per second and we started at 2 meters per second. And that happened over a period of 4 seconds. Then we'd do 8 divided by 4 here, and that would tell us that our average acceleration was 2 meters per second per second. That is to say that in every second, just those numbers, 2, 10, and 4. So that is to say that for every second that we would be moving across here, we would be increasing in velocity by 2 meters per second. 2 meters per second. Okay, and you could write that out as well by saying 2 meters per second. Okay, it's all the same thing, which is the same as saying 2 meters per second squared. Okay, so or 2 meters, 2 ms to the minus 2 on the s there. Okay, all the same thing. So, you know, that would be a situation of constant acceleration here. Okay, so let's take some back, see how far we can go. That doesn't like us going further than that. Okay, so this is a situation of constant acceleration. And that's what you deal with in physics, and that's where the SUVAT formulas come from, if you're aware of them. This is very different. But in our case here, our velocity depends on time, for example. So if I was going to do a VT graph in this case, well, it could be like this. Okay, as long as it doesn't go backwards, because that wouldn't be a function. You know, it could go, we're not sure what it's going to look like, in fact, but you know, it could be that we have a case where the acceleration keeps changing. So we accelerate to a maximum velocity, then we decelerate to a minimum to a low point for the velocity, and then we start accelerating again. Okay, so we can see that we're dealing with situations where the velocity is dependent on time, and likewise, the acceleration might not be constant. That will depend on time as well. It could be that it's constant, but you know, a lot of these cases you'll get quite complicated functions for s in terms of t. Right. So you should be aware though that this situation here could be changed into an acceleration time graph and a displacement time graph, an st graph if you like. Now I'm sort of adding a lot of thoughts in here. But let's just have a little look at the SUVAT equations. And the SUVAT equations are interesting for situations of constant acceleration. And they're basically saying the rearrangement of this, which is v equals u plus at. And this is a nice little bit of maths and a nice little exercise, in fact. And that's essentially saying y equals mx plus c. You know, your acceleration is your gradient. Your x is t in this case. And your c is the point on the axis where we start. So that's a really sort of simple formula, which is coming out from a rearrangement of our acceleration formula as well. Now, again, all I'm doing is just going into the SUVAT equations a little bit, just talking around them a bit. If you want to skip on the example, you're obviously welcome. Okay, so other things that you can get out of this, you might be aware that underneath the curve gives you your displacement. And although we're not proving that in this case, it's kind of fairly obvious if you come up with a case of saying, I don't know, if you travel at, let's say, 5 meters per second, so that's our velocity in meters per second there, for, let's say, 10 seconds, okay, and we stop there, then obviously we've traveled, so our time in seconds, obviously we've traveled at 50 meters. Okay, we've gone for each second, we've gone at 5 meters per second, and we've done that for 10 seconds. So area underneath a curve for a velocity time graph is the same as your displacement, in fact. And we'll formalize that later when we come up to doing the integration of velocity. It's going to give us S. The integration also defines the area underneath a curve. So we'll deal with that a little bit later on. Okay, so S here could be the area underneath this curve. Well, the area underneath the curve is a trapezium. So we can say the two parallel lengths, U plus V, times by the height of the trapezium being on its side, is equal to your S formula. Now you can get two other S formulas out by changing this into a rectangle plus a triangle, or by changing this into a massive rectangle, take away a triangle, and then you can get out another formula for V squared, which cuts out your T entirely. Those are the SUVAT equations, okay? And it's nice to know about them, but that's for constant acceleration. Okay, we're going to move on. Okay, so let's have a look at these questions then. And they say in the little box here, they say velocity is the first derivative of displacement, acceleration is the second derivative of displacement, or the first derivative of velocity. And then they formalize it in this little box here. They also note that when V and A have the same sign, the particle is speeding up. And when V and A have different signs, the particle is slowing down. Right, okay. When V and A have, that's actually worth talking about, okay? Because that's what we were mentioning by A being a vector quantity. And this word acceleration and deceleration being our sort of, we have the same word for the vector quantity as for the magnitude, in fact. Okay, so when V and A have different signs, okay, so let's think when we're going up a line, we're starting here and we're going up this line, and let's say that the velocity is positive. If the acceleration is negative, that means that we are slowing down bit by bit each time. So as A is negative. Okay, so if the original velocity is say 10 and A is -1, then we're slowing down by -1 for every extra 1 we add on to T. Now let's look at it the other way around. Okay, so that's deceleration. Okay, now let's look at it the other way around for the definition here, saying, well, if V is traveling this way, so V is negative, and if A is positive, okay, so if A for us is positive, then we can see that we're also slowing down. You know, if we're traveling backwards at 10 meters per second and our acceleration is 1 meter per second, then in the next second, we're going to be traveling at 9 meters per second backwards, or -9. So this is difficult in terms of the language, because although acceleration is definitely a vector quantity, when we're talking about something decelerating, deceleration is not a vector quantity. They're saying it's just talking about the particle slowing down. So this really needs to be analyzed through the questions, but they're definitely saying that deceleration is our magnitude of what's happening. Okay, it should become clear through the questions, to be honest. So, I mean, don't stress too much about this, but let's look at the questions and get plenty of practice. So we've got example 36. Here we go. And it says a particle moves in a horizontal line, so that the position from a fixed point after t seconds is s meters, where s of t is equal to this thing here, and t is measured in seconds. Did I mention about SI units? Forgive me if I've mentioned it already. SI units here, it comes from the French Système International, and we're generally using seconds and meters as our base units for these questions. But they could talk about kilometers and hours. They can mix it up a little bit. But if you're interested, here are the usual units which you're using in physics and often in most maths questions around the world. Okay, so let's have a look. What are we looking at? So find the velocity and the acceleration of the particle after 1 second. Okay, well, dead easy then, right? So v of t is just the derivative of this thing here. So we're getting nt minus 4t cubed. And we're also getting a of t here. So a is going to be 10 minus 12t squared. And then, of course, we want after 1 second, so we're just put 1 in there. So we're getting 10 minus 4 is 6 meters per second. That's meters per second, in fact, or you can write that, of course, like this. And we generally only put our units on right at the end. So we wouldn't want to put our units on at any point in between, because then your m and your s could seem like variables, and they're not. Okay, and for this one, we can put in our 1 again. So 1, and we can see that we're getting 10 minus 12, so we're getting minus 2 meters per second squared, or again, ms, and m divided by s squared. Okay, so that's part 1 done. Part A done, rather. Part B says determine whether the particle is speeding up or slowing down at t is equal to 1. So, well, since the particle is moving in a positive direction, the velocity is saying that we're increasing wherever we are. In the next second, we're increasing by 6 meters in that second, but also that by the next second, we'll be down to increasing by 4 meters each second. Okay, we'll be down to that because at this point, the acceleration is reducing our speed, or sorry, our velocity by 2 meters per second every second. So we are slowing down at this point, and we are slowing down because there's a change of sign between the velocity and the acceleration. Okay, so the particle is slowing down. The speed is reducing. The speed is reducing, not necessarily the velocity, because if it was the other way around, if this was negative and this was positive, then the velocity would be increasing, just less negative, in fact. Okay, so there we go. That's the little point from the book. That's this point, the last statement there from the red box. Okay, so determine whether or not it's speeding up or slowing down. It's slowing down. This. Okay, find the values of t when the particle is at rest. Well, it's at rest when there's no velocity, when it's not moving. Okay, so we need to find when is v of t equal to 0. That's part C. So we need to set 10t minus 4t cubed equal to 0. Now, we can obviously take the 4t cubed to the other side, divide by 2, so we're going to do 2t cubed minus 5t. And now we're going to factorize out the t, and we're left inside with 2t squared minus 5 equals 0. And then you're going to need to solve the thing inside as well. So we're getting three answers here. Now, it does say as well that t is greater than or equal to 0. So we're getting out, of course, t is equal to 0 from the first factor. From the second factor, we're getting 2t squared minus 5 is equal to 0. So from this one, this implies that t is equal to 0, but also this thing. So we can say t is equal to the square root of 5 over 2. Now, it can't be the negative there because again, t is greater than or equal to 0. So just the 5 over 2 square rooted, whatever that is. Okay, so just checking with the book then, we can see that we're getting the answer of square root of 5 over 2 is roughly equal to 1.58 seconds. Okay, so that's fine. Now, let's just clear this out. And let's look at this last question. So last question is saying, find the time intervals on which the particle is speeding up and the intervals on which it is slowing down. Now, for that, again, let's go back to that definition again. And the definition says the particle is speeding up when V and A have the same sign. So that's quite an important definition. Okay, and it's slowing down when they have different signs. Okay, and that's quite difficult to think about because it's not just when is it speeding up. If it's traveling in the positive direction, then that's obviously when the acceleration is positive. But when we're traveling in the negative direction, when the velocity is negative, then also we're speeding up when the acceleration is negative. Okay, so we need to think about the sign, essentially, of the velocity in various intervals. So again, let's just go back to, sorry, I lost this one. We've got 10t minus 4t cubed for v, and we've also got at was equal to 10 take away 12t squared, and we had in this time period the fact that the velocity was equal to 0 at 0 time as t is equal to 0, and also at the square root of 5 over the square root of 2, if you like, the square root of 5 over 2. Okay, so there's our two zeros for the velocity, but we also need to think about when are we going to get zeros for our acceleration as well. We need to consider all of the sign changes. So let's look at when the acceleration is equal to 0. So that's it. We need to solve this thing here. So we've got now 10 is equal to 5 is equal to 6t squared. So 5 over 6 is equal to t squared. And again, we can't have a negative value here. So we're going to get square root of 5 over 6. Now, I don't know where square root of 5 over 6 is, but I know that that's going to be smaller than this value here. So somewhere in the middle, we're also getting this square root of 5 over 6. So those are the key points that we need to check. And we need to sort of, a sign table is useful here. So we've got our t for certain intervals, and then we've got v, and then we've also got here the acceleration. So we don't care what happens before 0, but we definitely care what happens between 0 and square root of 5 over 6. And then we care about what's happening between these two as well. So between square root of 5 over 6 t and square root of 5 over 2. And then we care about what's happening on the other side. So when t is greater than the square root of 5 over 2. Okay, so those are the situations which we care about. Now, we know that the velocity function is, what are we getting here? We're getting a negative cubic, in this case, for velocity. And I know as well that this one crossed the axis at 0 and at the minus the square root of 5 over 2 and the square root of 5 over 2. And because I know that the graph has to be a negative cubic here, I know it's going to go through like this, like that. Okay, roughly. Okay, it's not be good, but it's going to go something like this. Now, I can use the properties of those graphs, but if I actually have to prove that, then I'm going to need to consider the concavity either side, or maybe just looking at the velocity in between this point and this point here. Now, the fact that I've got this graph means to say that I actually know that velocity, the velocity graph here, is going to be positive anywhere in this section here. So I know that this is going to be positive. I know it's going to be positive here. And then I know it's going to be negative afterwards. Now, that's how I'd do this one. You know, again, if you're asked to actually prove this in any greater extent, then you're really going to need to consider, as I said, consider what's actually happening in between those roots. So you can either check a value in between, given that this is a continuous function, that should be okay, or you can check the concavity at a point in between as well. Okay, or rather the concavity of S of t, sorry. So, right, anyway, let's not confuse anything more than it needs to be. Let's look at A then. So for A, what's the graph looking like? Well, this is a negative quadratic. I know that I've got two coordinate points where A of t is crossing the axis here, and it's actually going to be plus or minus this thing here. So I know that A of t, this is our B of t, and I know that A of t here is going to be a negative quadratic, and it's going to be going through minus root 5 over 6 and plus root 5 over 6. So what's happening from here to here? Well, it's coming like this, A of t. So we can say that A is positive there, and then we can see after that it's just going to be negative, because after this point here it just decreases. So we're negative and negative. Okay, so now we can actually say what's happening. When is this particle speeding up? Well, it's speeding up when we have a positive acceleration on a positive velocity, and also when we have a negative acceleration on a negative velocity. So that's when it's speeding up, during this and this interval, and then we're slowing down in this interval here. So it's slowing down when we have a positive velocity and a negative acceleration there. So this question is a fair bit harder than you might first imagine. Okay, and I think this is the first time that I've agreed with the book in saying that a sign table is actually really useful here. Okay, let's have a little look. Yeah, they're coming up with a sign table as well. And they haven't started thinking about the concavity of each of these things. They've just made it pretty straightforward with that sign table. And I've made it more complicated by considering the shape of these graphs as well, just to make sure that I've got my signs correct in each of those periods. Okay, well, let's have a look at the exercise. We've got 4T here. I think that's the first time that any of the units has gone up to exercise T. So we've got 7 questions there. And then next time round, we're moving on from the applied type of questions, and then we're talking about implicit differentiation and techniques of this. But then the questions will become applied when we start talking about related rates of change. But implicit differentiation is going to be a new technique to learn before we get to the applied type of questions. Okay, so thanks for listening in. That was useful, and I'll see you back next time.